We can investigate graphs using Desmos. And what I want to do is look at this specific example, g of x equals 1/4 x squared plus 2.2x plus 3.2. And I want to answer these questions about the graph using Desmos. So first off, opening up Desmos, we need to put in the equation, g of x. And I'm going to use function notation here, and I'll show you why in a moment, equals 1/4. And I want the x to be out of the fraction, so x squared. Plus 2.2x plus 3.2. Double check that you have put the equation in correctly. What we can see here is the typical parabola shape. I'm going to just center this in my screen a little bit. And then I'm going to click back on the graph because Desmos will always show us some important points on any graph, including the vertex. So if we look at the very bottom of this graph, Desmos has a gray dot, and if I click on it, I can see that the value of the vertex is -4.4, -1.64. So I have the coordinates of the vertex. It will also show me intercepts, like the y-intercept. There's another gray point there, which I can click on, and I see that the y-intercept is 0, 3.2. X-intercepts also have gray points at -1.839, 0 and -6.961, 0. These x-intercepts are most likely rounded. You see how they're out to the third place? These were probably rounded off by Desmos. It often rounds to the third decimal place. Other questions we can answer by looking at the graph is the domain and the range. The domain is going to be the set of all x values on the graph. Remember, this graph is going forever in up and out. So because it's going forever out in both directions, both on the left side and on the right side, that means that the domain is going to go from -infinity to infinity. That is not true of the range, because even though the graph goes up forever, it doesn't go down forever. And the vertex is a good place to see what's happening with that range. This is the lowest point, and the y value in specifically is the lowest y value. So the range is going to go from -1.64 up to infinity. The last two questions have a little bit to do with understanding function notation. The next question is g of 3. Well, because I've listed this equation in Desmos as g of x, I can actually have Desmos evaluate functional values for me. If I put in the next line g of 3, it will calculate for that and show me the value of 12.05. You can put in any functional value this way. So g of 5 is 20.45, g of 123 is 4056.05, but we were interested in g of 3, so I'll go back to that one. So you can, if you list your function in functional notation, you can then evaluate it at different points along the way. The last question is to solve g of x equals 5. Now we have to do a little extra to solve this one. We need to actually look at where the y value or the output is 5. And the easiest way to do that is to type in a horizontal line at y equals 5. When we do that, we can actually see exactly where our function is going to have an output of 5, because it's going to be where it crosses this horizontal line. So there's one point where it crosses there, and then it crosses over here at another point. Remember, Desmos will show you intersection points as gray points, and so you can click on them to get these specific values. So my answer to this last question would be that the x values would be -9.554 and 0.754. Those would be the x values when the output is 5. So here are all those values that we talked about when we looked through Desmos. I just wanted to have them all written out nice and neat so that you could double check what you wrote down yourself. Let's use Desmos to investigate a quadratic application. In a race, a car drove through the starting line at a speed of 4 meters per second. It was accelerating at 2.7 meters per second squared. Its distance from the starting position can be modeled by the function below, where t is the time in seconds. When will the car be 242.4 meters away from the starting point? Now the function is d of t equals 1.15 t squared plus 7t. Let's graph that in Desmos. We can use function notation, d of t, and actually use t. When we use function notation, Desmos will understand that to be the input variable and graph it on the horizontal. 1.15 t squared plus 17. So here we have the graph, and we can kind of see that it's a quadratic, but we can't see the base or the vertex, and we maybe aren't going as high as we need to, because remember it asked us about the car being 242.4 meters away from the starting point. So we really need to change our window. So go over to the controls for graph settings, which is the wrench in the upper right hand corner. Click on that, and let's open this up a little bit better. Now we definitely know we need the y-axis to be different. We need to go down lower to see the vertex, and we need to go up higher to get up above that 242. So I'm going to go up to 300 on my y-axis. Now when we do that, we also see that you can't see, the parabola gets so wide it's hard to see. So let's change the x-axis and make it go, even though we're graphing with t, technically in the application, we're still thinking about this in the grid as x. I'm just going to make that 20, and now we can see the graph a little bit better. Now this is an application, so technically I'm really only interested in values that are positive. So I'm just going to move the graph so you're really just seeing positive values of the graph. When we graph this, we're seeing, if we click on it, we can see that we have an x-intercept here, and it is also corresponding to a y-intercept. The graph is going to continue up from this point on, so we don't have any other significant to our application x or y-intercepts. What we want to answer, though, is a question about when the car will be 242.4 meters away from the starting point. Now, to find when, we're finding time. So the 242.4 is an output value. So if I want to find that, I'm going to say y, which is the output, equals 242.4. What's nice here on the graph is we're going to get the horizontal line of 242.4, and that will show us any intersections with the function we had originally, which I can then highlight. So it turns out that when the x value is 11.79, or remember this is a function where the input is t, so really that's t equals 11.79, then we have a distance from the starting point of 442.4. So our answer is that it's going to take 11.79 seconds to be that far away from the starting point. And here we have the answer written out in words. The car will be 242.4 meters away from the starting position after about 11.79 seconds, which we were able to see from the graph in Desmos.